Hello students, I am Professor Navneet Kaur from EC Department, SIRT College, Bhopal. Today I will be taking lecture on subject digital communication. The topic which I will be discussing is Quadrature Phase Shift Keying QPSK system. In this lecture, we will discuss the basic concept of QPSK system, the QPSK transmitter, and the phasor diagram of the QPSK signals. Now first we will see what is QPSK system. In QPSK or quadrature phase shift keying, two successive bits in the data sequence are grouped together and transmitted. We have seen in BPSK system when a data stream whose bit duration is TB is transmitted, the channel bandwidth is 2FB, where FB is equal to 1 upon TB. But in QPSK, as two bits are transmitted, we allow bit to be transmitted using half the bandwidth because it reduces the bit rate or the signaling rate, and thus the bandwidth of the channel is reduced. The combination of the two bits form four distinct symbols. When the symbol is changed to next symbol, the phase of the carrier is changed by 45 degrees. Now here we can see the block diagram of the QPSK transmitter. Now first we have assumed that in every case, the active edge of the clock waveform is the downward edge. Here we can see the toggle flip-flop. The toggle flip-flop is driven by a clock waveform whose period is the bit time TB. We can see in this waveform. The toggle flip-flop generates an odd clock waveform and an even clock waveform. These clocks have periods 2 TB as seen in the waveform. The active edge of one of the clock and the active of the other are separated by time period, which is bit time period TB. The bit stream BT, we can see here, is applied as the data input to both type D flip-flop, one driven by the odd and one driven by the even clock waveform. The flip-flops register alternate bits in the BT and hold each such registered bit for 2-bit intervals, that is for time period 2 TB. Here we will see the waveforms in the QPSK transmitter. Here we can see that this is the basic clock waveform which triggers the toggle flip-flop. Two clocks are generated, one is odd clock and another is even clock. We have numbered the bits in BT. We can see the bit sequence in BT. We have numbered the sequence. We note that the bit stream B0T, which is the output of the flip-flop driven by the odd clock, registers bit 1 and holds that bit for the time 2 TB. Then it registered bit 3, then it holds for time 2 TB, then it will register bit 5 and so on. Whereas the even bit stream BET holds even numbered bits, that is 2, 4 and 6 and so on for time 2 TB. The bit stream BET, here we can see in the block diagram, it will modulate the carrier root PS cos omega naught t, whereas the bit stream B naught t is superimposed on the carrier root PS sin omega naught t by the use of the two multipliers, or we can say balanced modulator. These signals, which are SCT and SOT, are then added to generate the transmitted output signal VMT. So VMT can be given as root PS B naught t sin omega naught t plus root PS BET cos omega naught t. So here we have seen ST, which is the resultant QPSK signal, is generated by the addition of S0T and SET, which is given by this expression as discussed earlier. Now we'll see the phasor diagram of the QPSK signal. Since here two bits are grouped together and are transmitted, so we will have four combination of the bits. When B0T is equal to 1 and BET is equal to -1, in that case, we will have two combination. That means B0T is 1 and BET is equal to -1. That means we have root PS sine omega naught T minus root PS cos omega naught T. So here we can assume the direction of cos omega naught T as the standard direction here shown in this phasor diagram. Root PS sine omega naught T is given by the direction which is given by this downward direction, root sine omega naught T. So minus sine omega naught T will be given in the opposite direction. So here we can see for bit combination B0T is equal to 1 and BET is equal to -1. Here we will have the resultant phasor which is represented by ST, which will have phase difference of 45 degree from the reference direction of cos omega naught T. Similarly, all other three phasors are also represented here. So we can see that the four signals have been represented as phasors. They are in mutual phase quadrature. These four possible output signals have equal amplitude, which is root PS, and they are in phase quadrature, and they are identified by the corresponding values of BOT and BET. In the waveforms, we can see that the end of the each bit interval, either B0T or BET can change, but both cannot change at the same time. So this QPSK system is called offset or staggered QPSK system, which is known as OQPSK. After each time TB, the transmitted signal, if it changes it will change its phase by 90 degree rather than by 180 degree, which is done in BPSK. So here we can see the four combination of the bits B0T and BET. So we will have combination 10, 00, 01 and 11. Corresponding to these four combination, we have four symbols S1, S2, S3 and S4. So there are four symbols and the phase is shifted by 45 degree or pi by 4 for each symbol. So for S1 we have phase shift pi by 4, for S2 3 pi by 4, S3 5 pi by 4 and S4 we have phase difference of 7 pi by 4. And since here B0T or B0ET cannot change at the same time, this QPSK system is known as offset QPSK system. Now this is all for today's lecture. Thank you.